Hi, this is Team 5773 Ink and Metal, and we are presenting our Control Award video which encompasses our driver-controlled enhancements, autonomous paths, and key algorithms in our code. Here is an example of our 4-ring autonomous in action, and we shoot the 3 preloaded rings in the high goal, then we do immediately intake 3 of the rings in the 4 stack, and shoot one of them and then get as close as possible to the high goal to ensure consistency of the rings. Then we drop the first wobble goal in the correct drop zone and move in the most efficient manner to get to the second wobble goal, pick it up, drop it in a similar spot, and then move forward to park on the launch line. What allows us to be so efficient during the robot match is the use of odometers, 2 parallel odometers and 1 perpendicular odometer, which work together to determine the robot's position on the field relative to its starting position as well as its angle throughout the match. The first use of odometry in teleop on our robot is automatically returning to the shooting position. In this clip, the robot intakes 3 rings, and with the click of a button, the driver can automatically return to the shooting position, eliminating any room for error. In this scenario, our localization system is quite similar to Tesla's auto drive system. Now let's suppose this position is the robot's starting position, and the driver drives back to somewhere in the back of the field. And let's say the driver clicks a button to get back to that position. The robot will do anything to get back to that position using heading and translational PID. In our current robot, we have the battery placed at the bottom, which is similar to electric cars such as Tesla right now, where the battery is also at the bottom, and this helps the robot have a lower center of gravity, in turn helping the odometers be more accurate. And this strategic battery mount placement is quite unique for our robot and our team. In order to map out our autonomous paths ahead of time, we used a virtual robot programmed in Kotlin in order to do roadrunner trajectories, which we would later be able to directly translate into our in-real-life robot. In this year's Autonomous, using computer vision to find the number of rings in the starter stack is crucial. In order to accomplish this, we mounted a Logitech webcam on our robot that uses a custom easy OpenCV pipeline made via a grip software to return the height of the stack after singling out any other elements in the frame, making it extremely consistent. Here you can see a clip of our outtake shooting 3 rings in the high goal in less than a second. For this to be possible, we had to do sincere PID tuning, where the velocity of the outtake motors is equal to the target velocity. As you can see, the purple line nearly matches the red line always through the use of PID, proportional integral derivative controller. And although sometimes it is a bit lower, that could simply be just because of voltage issues. The entire power shot process is automated, as the driver only has to click one button to shoot all 3 power shots through finite state machines. A distance sensor at the top of our transfer allows us to detect the number of rings that we have intook so far, and when 3 rings have been detected, the outtake automatically starts revving up. Stakes. And lastly, here is the driver dropping the wobble goal, and through a multi-step algorithm, we minimize the number of buttons that the driver has to use.